So how do we draw reciprocal graphs? So we're going to draw one on function x. Well, if we've got our original function, we can observe certain things. If function x is equal to 0, and we know we can't have 0 on the bottom of the fraction, we know we're going to end up with a vertical asymptote. Here's random graph. And I've tried to draw a random graph which has got every possible sort of feature. We've got a horizontal asymptote in there, we've got turning points, we're negative in some parts, positive in some. So what we're saying is each one of those x-intercepts will turn into a vertical asymptote. So we know that. Now as function x approaches infinity, then the reciprocal would approach 0. So that means the asymptotes on the original graph, the vertical asymptotes, will become x-intercepts sort of. So over here on the left there we've got a vertical asymptote. That's going to become an x-intercept sort of. It's actually a point discontinuity. Because remember, you're drawing the graph of 1 on function x, but we said for function x it's undefined. It can't all of a sudden become defined. It's the difference between drawing y equals 1 on x and drawing the line y equals x. Right? The reciprocal of 1 on x, yes, that is x, but the reciprocal of 1 on x has a point discontinuity at the origin, as opposed to just the line y equals x. Right. Now 1's an easy one for the reciprocal, because if you turn 1 upside down, you get 1. So that's always good to work out where 1 is on your original graph, because those points will remain. And the same with negative 1. I'm assuming that turning point's at negative 1 for the sake of this example. Now, the horizontal asymptote here is smaller than 1. If I turn a number smaller than 1 upside down, I'm going to get a number that's bigger than 1. So on my new graph, I know it's above 1. So I've drawn it in, I've just estimated, but I've put my red horizontal asymptote there above 1. When the original function is increasing, the reciprocal will end up decreasing. And the reason for that, if you differentiate 1 on function x, you get minus the derivative on the function squared. Well, the function squared is going to stay positive. So it's minus the derivative of the original function. So if the original function has a positive slope, well then reciprocal minus the derivative must have a negative slope. So if we talk about when the graph's going up or down, increasing or decreasing, when the original graph is increasing or going up, we know our new graph will be decreasing and going down, and vice versa. The sign's not going to change. I mean, turn a positive number upside down, it's still going to be positive. Turn a negative number upside down, it's still going to be negative. So again, let's go back to this graph. I could draw in then sections where my new graph is going to go. Okay? Let's start from the left-hand side until we get to the point 1. That's why 1's important, because we know it's going to stay there. But as we start from the left, I've got something that is smaller than 1, but then stops at the horizontal asymptote. So if I turn it upside down, I must get something bigger than 1, but it will stop at the horizontal asymptote. I then go from this point here at 1 all the way to the vertical asymptote. Now, it's always above 1 and stays positive. Therefore, when I turn it upside down, it must go below 1 and stay positive. Then I get to our pretend x-intercept, if you like. I now have, from the asymptote to the blue curve, it's a number, well, it's smaller than negative 1. So therefore, when I turn upside down, it must be bigger than negative 1. I prefer to think of it as below and above. I just find that easier. So if I look at the picture, the blue line is below 1. Therefore, when I turn upside down, it must be above 1. But again, it's got to stay negative. Okay, then from that point to our vertical asymptote here, it's above negative 1. Turn upside down, it must go below negative 1. And I keep doing that for each of those sections, and I can work out where the curve is going to travel. Now going back to the derivative, remember minus the derivative on the function squared. So the original graph would have stationary points when the derivative is equal to 0. So therefore my new graph would also have a stationary point because it's minus the derivative on the function squared. So it's going to be minus 0. Well, it's still 0. So original stationary points will remain. Now, the y value might change because it's going to be 1 over. But the actual x location for the stationary point will still be the same. So I know up here, the maximum turning point, it's above 1. So it'll go below 1. Instead of being concave down, it'll go concave up because instead of increasing, it's decreasing, and so on. I've just estimated again. I'll put it down here. This one on the right, the minimum turning point, well, I've assumed that's -1. It's going to stay there, but the minimum turning point will turn into a maximum turning point, which allows me now to draw the graph. So the red curve there, it goes through all the points that I know, it stays in the regions I know, bends towards the asymptotes, all those sorts of rules we know it has to obey. Let's get rid of everything else, but there is our graph of our reciprocal curve. All right, so that's how we do reciprocal graphs, and there's a handful there. 1, 2, 3, 4, 5, handful and 2 fingers on the other hand of questions to do.